Okay, great. Thanks a lot for the introduction, and I'm very happy to present at this workshop, and I'm really sorry that I couldn't come in person. I really hope that I can come to the second workshop in the beginning of June, though it's, well, pending visa still, so we'll see whether I will be lucky enough. Yeah, so today I will be speaking about something which is definitely multivariate, but not but fully Euclidean and not functional. However, there will be some connections with what Mark was telling in the lecture before the lunch, as you will see later on. And also, I think my talk will give a nice connection between the topic of this workshop and the topic of the next workshop, which will be on calibration. So basically, I will be talking about conformal prediction. So, and I'm sure that probably all people, or majority of people in the audience know what is conformal prediction, but I will give a brief introduction so that we are sure that we are on the same page. So basically, I will be operating in this type of a standard supervised learning, and in all my talk, I will assume that I already have some predictive model. It can be a regression model, it can be a classifier, whatever. And on top of the model, I will be given a set of n calibration samples from a data distribution equation. And my goal will be to construct the confidence set for a given miscoverage level alpha, such that the probability that the new observation yn plus 1 comes to this confidence set with the probability ideally as close as possible to myself. And conformal prediction is a certain framework which allows to achieve that, and importantly, with almost no assumptions on the distribution Pxy. So, and conformal prediction was developed in mid-90s by Vladimir Vovk and his collaborators, and it was a certain extension of rank tests which are common in non-parametric statistics. So why people currently use conformal prediction quite extensively? In particular, it became popular in machine learning community. There are multiple reasons. First of all, the conformal prediction methods, which I will introduce on next slide, they're easy to understand and implement. They usually work on top of any like black box machine learning model. And you usually don't require any additional training, so you use only some very simple operations like quantile computation. And the methods are flexible, they can be applied to any model. And I think that's some reasons why the conformal prediction methods were gaining increasing popularity. So for example, Vladimir Vovk's book on algorithmic learning in a random world, in the recent years, you see it has an exponential increase in citations, so everyone is using these methods. Let us then discuss what the method is exactly. As I said, we are given a calibration set of endpoints, and then the next ingredient which we need is so-called score function. So for given x and y, we want to compute score, which basically measures how the prediction at this point aligns with the true label. So for example, for regression, it can be just absolute difference, so the absolute value of residual. And for classification, there are various choices. One of them is 1 minus probability of a true label given by a classifier. And given this data set and scores, conformal prediction just considers the empirical distribution of the scores. Okay, so there is empirical measure given on the slide. And eventually what you do, you compute 1 minus alpha, well, to be precise, slightly shifted quantile, and your confidence set is a set of all labels such that the score function for these labels is smaller than the quantile. So extremely simple procedure. you have calibration data, you have model, you compute score functions, you compute quantile, and then for every new input, you get confidence sets. The question is whether this confidence set is useful, and I think the attractive feature of conformal predictions that you get very strong guarantees. So basically, what you achieve that the probability that you belong to this confidence set is greater than 1 minus alpha and smaller than 1 minus alpha plus the remainder term of the order of 1 over n. So that looks better than the majority of guarantees we have in statistics, because the standard rates in statistics are usually of the order, in parametric statistics, are of the order 1 of square root of n, 1 over square root of n. Here we have 1 over n. So it looks nice. Small comment here that I'm speaking about a particular variant of conformal prediction called split conformal prediction. There exist more general algorithms like which are slightly different. Okay, so looks very good and probably too good to be true. So how is it possible that we construct something with strong guarantees, and with score function which was completely arbitrary? Well, in fact, this method will work well if the score function is meaningful. If score function correctly ranks the inputs from like the lowest to highest magnitude of an actual error, then your result will be valid and good. However, if score function is inappropriate and doesn't lead to any meaningful ranking, then these sets will be useless. So for example, if your scores are like pure random noise, then the resulting sets will contain just a random sample of the label space, which ensures the marginal coverage. And the guarantees are nice, but the actual practical applicability pretty much depends on the score function which you are using. Yeah, so the other thing which was not discussed yet is that the guarantee which we considered was completely marginal. It was averaged over new x, new y, but also over the calibration data set D. If you consider the miscoverage rate conditioned on a calibration data set, then the previous guarantees just says you that expectation of this guy has this nice bounds between alpha and alpha minus 1 over n plus 1. The distribution of alpha itself will be a beta distribution with the following parameter, which means that in fact alpha will concentrate, empirical miscoverage will be like a random variable which is concentrated near the true miscoverage rate with the remainder term of the order 1 over square root of n. So to reinforce, we have this nice bias of the order 1 over n, but the standard deviation is of the order 1 over square root of n. So there's no free lunch and no contradiction with like classical statistical results here. All right. So as discussed, these guarantees are marginal. So they're averaged, or the probability is taken with respect both x and y. However, we might want something stronger. We actually might want some guarantees for a particular point x. So, and ideally, what we want to achieve is conditional validity. So we take a particular x, and we want that y corresponds, and y is contained in the confidence set for that x. And that's obviously much stronger guarantee. And it was shown in the literature that it cannot be achieved without like imposing some further assumption about the data distribution. So that's impossible to achieve this guarantees distribution free. I would also comment that for the practical purposes, it's sufficient to construct sets which will have approximate conditional validity, and ideally we want them to achieve like exact validity in the limit of a large sample size. That will be a goal of this talk. So we will At the end, we will construct some prediction sets which will be approximately conditionally valid, and also like in the limit of large sample size, and they will give exact validity. Few words about conditional coverage. Probably the most famous methods which targeted certain type of conditional coverage is methods as a methods based on quantile regression. So basically, what you do is a quantile regression for the desired level, and then you kind of conformalize this method. In particular, you may consider the score, which is written in the center of the slide. And for this method, many nice guarantees can be given. So in particular, it was shown by Sessi and Candes that the constructed intervals, they converge to the narrowest possible intervals under mild assumption. What is a little bit problematic about these methods based on quantile regression, that they are pretty much focused on one-dimensional case. So we consider regression in one dimension, and in the case of some more complex distribution in a Y space, they might not work. How can you go from one-dimensional to multi-dimensional case? Well, there exist some obvious choices. For example, one can construct box-type prediction sets. So basically, you consider the maximum deviation of between Y and predictor for maximum over the dimensions, and that gives you these rectangular prediction sets. Or you may consider ellipsoidal prediction set, and so on. However, such prediction set might be suboptimal if the data distribution has a complicated shape. For example, on the picture on the left, we have like this axis is X, and then we have two-dimensional Y. And in a Y space, the data distribution is this two moon, is represented by two moons. And we see that like oracle prediction sets based on the true data density, they are like nice and small, but have a peculiar shape. While if you construct rectangular sets, they obviously will be very large, and not very useful in the sense that, yeah, you will achieve nice coverage, but with very large sets. Possible ways to move forward, and here we see some connections with the previous lecture by Mark, is usage of multidimensional ranks based on optimal transport ideas. And just recently, this year, we have already two papers on this topic by a group of Marco Couturi and by a group of Claire Boyer. And in these papers, they consider various variations of this multi-dimensional runs based on optimal transport, and it works pretty nice, and I think it's a good direction to develop further. However, in this talk, we will look on a little bit different ideas. So, okay, that was an introduction. Now we will come closer to what we were actually doing in this work. And as I said, conditional coverage, it's our goal, but it's impossible to achieve without imposing some additional assumption on the data distribution. And what we will do in this work, we will consider particular assumptions that we have certain approximation of our true data distribution. So we assume that for a given point, we have a generative model that can produce samples. So we have this distribution P of Y given X. And our starting point will be another conformal prediction method, which I think has a very interesting idea. So the method works as follows. It's called probabilistic conformal prediction. It generates several samples from the generative model. So for a given X, you generate several samples. It might be 5, 10, 20, whatever your budget is. And then we will construct prediction sets of a very particular geometry. The sets will be a union of both centered in the generated Y's. So, and both are in the output space of a radius T. So, and for such a construction, well, first of all, it obviously kind of captures the geometry of a of data distribution, and that's why it's pretty flexible. Also, it's straightforward to define the score function like smallest radius such that the label is contained in this confidence set. So probably more like illustrative. You generate, for example, five samples, as here you see black dots, and then your confidence sense becomes the union of these balls. And then the goal of the conformal prediction becomes to just select the radius t, which will ensure the marginal coverage, and it can be done by a standard conformal prediction set. So as a result, for example, for that toy problem with 2 moons data set, the prediction set by PCP becomes, they look like the sets on the right. Not super nice in terms of continuity and so on, but capturing geometry much better and obviously having much smaller volume than the rectangular or the ellipsoidal sets in this case. All right, this method is nice and it kind of targets the conditional coverage because it considers the distribution. However, we're still interested to something where you can prove the conditional coverage and where you can ensure it at least approximately. So, and in this work, we will try to construct the set which is conditionally approximately valid for any x. We can use general score functions, but we have the score function of PCP in mind as like a good example of a method which will be constructed. And we want to use the generative model. So, okay, let us discuss how can we achieve that. First of all, if we have access to the true data distribution, like not to the approximation, but to the true data distribution, that obviously we can construct the set of the optimal size. So imagine you have a family of sets parameterized by t. Then we can construct the set of optimal size just as a minimal radius such that we exactly have a coverage greater or equals than 1 minus alpha. Well, on one hand, it's great. On the other hand, we don't have true pi in practice. We need to do something about that. And the immediate idea is, well, let us plug in the approximation here, right? So we have approximation, we put it there, we get the radius, that's the result. You will have certain approximate conditional guarantees, which will be depending on how well approximate distribution approximates the true one. However, you will totally lose marginal guarantees because, well, there is no conformalization in any sense. So, and our main innovation in this work will be that we will conformalize these probabilistic sets in a certain sense, and we will achieve the true marginal coverage. So, okay, few words about our construction. So again, we have the sets R parameterized by t, and we assume that the set size increases with t, and for sufficiently large t, we can cover entire output space. And our score function will be the same as in PCP, so the minimum t such that the value y is covered by the set. And what PCP does, it applies the classical conformal prediction method, so basically just computes the quantile of the scores. So what we will be doing the following. We will introduce a transformation function for scores. So we will have a function f, which transforms scores v, and it parameterized by a certain parameter tau. Examples of such functions include, for example, the product and the sum, but you may consider different examples. And what we will do, we will first do the same what you would do if you just have a density and don't know about conformal prediction. We will define the optimal radius, tau, for a particular point x, such that we get the right coverage according to our approximate model, okay? So that's tau, which ignores any conformalization, which just uses the approximation. Then what we will do, we will construct transform scores. We will transform vk with function f and taking the particular tau. So the tau you can compute for every point, having tau as a parameter. So it's a little bit hard to understand what does it mean, but I think a more explicit example, and one of which we consider, is that just you divide v, the initial scores, by this tau. So essentially, depending on the size of the set, you either make scores smaller or larger. And for this scores, this transform scores, we compute quantile of them here, and then apply the forward transformation. So here was the inverse transformation, so it was division, for example, and here will be multiplication. Okay, so now I will repeat the idea, and I hope it will make clear what we do. So we have the family of sets R, and for each point in calibration data, we compute a score, and we compute the optimal radius according to a generative model. Then we compute transform scores, compute the quantile. That will be our threshold for conformal prediction. Finally, for the new test point, x, we compute again tau from our approximate model, and we compute the final set based on the quantile. So that's the algorithm, and we call it CP2 algorithm. All right. Well, I probably won't discuss assumptions in detail. There are certain technical, not very restrictive assumptions for our theory to work. And we get the following results. The first result is that we ensure exact marginal coverage. So essentially the same guarantees as a standard conformal prediction. So it's literally the same. And second, we ensure approximate conditional coverage. So basically, if you bound the total variation distance between the true data distribution and the approximate one, you bound it for a given n by Rn, then the deviation of our coverage from 1 minus alpha with high probability is bounded by square root of log n over n plus this term Rn, which depends on the quality of approximation of our approximate distribution compared to the true one. So that's, I think, kind of a nice result, because you have explicit dependency on the quality of your approximation, and also you have this rate 1 over square root of n, which, as I discussed in the beginning of the presentation, is kind of a right rate for the deviations of conformal prediction. Yeah, we also have some experimental results, which I mean, we consider many different data sets, and we looked on certain approximations of conditional coverage. I'm not sure that it's very easy to see something here, but our methods, different variations of our method, are this red and purple ones, so they're in the middle, and in the many cases they're kind of better. You see they have a better conditional coverage and sometimes smaller variance than, for example, the methods based on quantile regression. So that's, I wouldn't say that this method is like some ultimate method which one should use in any application, but in certain scenarios it definitely gives benefits in terms of coverage, in terms of set size. I'm not giving a set size here, but we have it in the paper and so on. All right, so to conclude, so what we did, we used estimator of a conditional distribution within the conformal prediction framework, and our aim was to achieve conditional coverage. Our proposed mechanism was exactly to conformalize this estimator to ensure marginal validity and maintain conditional validity. And basically, if our estimator is good, then the proposed method will give approximately conditionally valid prediction sets. That's all, and thank you for your attention, and your questions are very welcome.
Thank you very much. We are a bit short of time, so just one question could be. Okay, if not, can you just come back on the condition for the quality of your estimator?
This one.
Yeah.
Yeah.
Okay, so can you explicit? So this is total variation.
This is total variation distance. So.
Yeah. Can you explain?
That's a good question if you can do something better than total variation here, but currently we have with total variation.
Okay, just wanted to have the intuition behind, but if it's too long.
You mean intuition? Why is total variation here?
Yeah. If you how.
Yeah, basically, when you prove it, you consider like you consider like true distribution and approximate distribution, and then you see probabilities of some sets, and then total variation like as a difference pop-ups naturally.
Okay, thanks. Okay, well, I think it would be interesting to discuss with you about the nature of the sequence Rn, but I propose that if people are interested, try to get in touch with you online.
Absolutely, yeah. If any questions, please contact.
Thank you very much.